Hello everyone, welcome back to the video lecture series on engineering hydrology with me Nihal Naveen. Hope all of you are doing fine. In the previous video we started with hydrological cycle and parameters part 4. In that we covered how to measure evaporation and we also did some theoretical study. Okay. In this video we are going to start with some numerical problems regarding calculation of evaporation, and we'll also be moving on to other components of hydrological cycle like the transpiration and evapotranspiration. So let's begin hydrological cycle and parameters part 5. Now methods to minimize evaporation. Okay. Now how we can reduce this evaporation? First is by reduction of surface area. As we know that if we go on increasing the surface area, then evaporation increases, as surface area is directly proportional to rate of evaporation. So if we reduce the surface area, evaporation decreases. Second is by putting mechanical cover, like sometimes we can put some screens or some other type of objections so that it can reduce the evaporation directly. Third is by using some chemical cover like sterile alcohol and cetyl alcohol. Now you just have to remember these two names, sterile and cetyl alcohol. They act with they actually form a layer over the water surface, and they don't allow the heat energy to come out of the water surface. Okay, so this might be helpful in minimizing or curbing evaporation. And the third is, and the last one is increasing salinity. As we already know, we go on increasing the foreign substances. We have seen that it decreases the rate of evaporation. Just as we saw that in case of sea water or ocean water, its rate of evaporation is less than that of lake water. Why? Because its water is saline or soluble salts are present. So if we increase the salinity value, then evaporation increase. Rate of evaporation decreases. Okay. So in this way, these are the methods by which we can minimize the evaporation rate. So let's take on some numericals from previous year GATE. This question was asked in the year 2015. Let's read this. The average surface area of a reservoir in the month of June is 20 km square. So area is given as 20 km square. In the same month, the average rate of inflow is 10 meter cube per second. So here the rate of inflow is given as in volume, that is 10 meter cube per second. So we can divide by area to get the depth. Outflow rate is 15 meter cube per second. Monthly rainfall is 10 centimeters. Now precipitation is given in depth, so 10 centimeter. Monthly seepage loss is 1.8 centimeter, and the storage change is 16 million meter cube. Now 16 million meter cube, it is not mentioned whether it is positive or negative. That means if the level is increasing or decreasing. So accordingly, when we go on solving the problem, we can get this value. If evaporation comes positive, then we can assume that accordingly we can assume. Okay, so evaporation loss should not be negative actually. Okay, so just solve this question. We know that this is the problem of water budget method. So we know that firstly precipitation value plus volume or depth which is incoming, surface inflow, okay, VIS plus anything more is not here, groundwater flow is not here, so directly it will be equal to outflow rate, that is VOS plus seepage loss, okay, loss plus storage delta S. Okay, now this delta S we can assume anything, it may be, here we are not knowing now at present whether it is positive or negative. So let's solve this. Precipitation, it is given as 10 centimeter. Okay, so it is monthly rainfall. This also you have to notice. So here we have to calculate the rainfall for the whole month. So average rate of inflow is 10 meter cube per second. So we have to convert this into monthly rainfall, monthly volume. So 10 meter cube per second. So this will be converted into 30 days, because there are 30 days in June, into 24 hours into 60 minutes into 60 seconds. Okay, divided by area, 20 kilometer square we have to convert it into centimeter. So 1 kilometer is equal to 10 to the power 5 centimeter. So centimeter square we have to cover. So 10 to the power 10. Okay. This will be equal to VOS. This will be 15 into same 30 into 24 into 60 into 60 divided by same area 20 into 10 to the power 10. Okay. Plus loss. Loss is given as 1.8 centimeter. Okay. And delta S. Delta S, let's assume, now we keep it for safe. Now this, when we solve it, we will get it as 10 centimeter plus this value will come around 129.6. Okay. And this value will be 1.8 plus this value finally we will get as 194.4 plus delta S plus evaporation loss that we have to calculate. Okay. Now when we solve this, we will find that if delta S we are taking positive, then EL will come negative. So we have to assume that this 16 million meter cube, you can just solve this 129.6. This is 139.6 minus 1.8 minus 194.4. Okay. This you can see here that this value is coming negative. Okay. So if delta S becomes positive here, then again it will come on the left hand side, it will become negative. So EL will be negative. So here delta S has to be taken positive. So this will be delta S, it is given as 16 million meter cube. Again you have to convert it into centimeter, that is 16 into 10 to the power 6. This is in meter cube divided by this you can convert into 20 into 10 to the power 6. Okay. So this 16 million meter cube, so this is converted into meter cube, and then 20 this is actually in this we are converting into meter, then we have to multiply it by 100. Okay. So this what we will get 20, this will be 80. Okay. So delta S we are taking negative here plus EL. So when it comes here, it will become positive, and finally we will get the EL value as 23.4 centimeter. Okay. So the correct option is option D. Okay. I hope this is clear. The only key point was here that delta S value we have to evaluate whether it is positive or negative. Now the second question, this question was asked in the year 2003. The plan area of reservoir is 1 kilometer square. Now plan area is given as 1 kilometer square. Water level in the reservoir is observed to decline by 20 centimeter. Now it is given delta S is negative. Okay, decline. In a certain period, during this period the reservoir receives a surface inflow of 10 hectare meter. Now this hectare meter, it is actually, we will convert into meter cube, this is actually volume. And 20 hectare meter are abstracted from the reservoir for irrigation and power. This is the outflow. The pan evaporation is 12 centimeter and rainfall is 3 centimeter respectively. The calibrated pan factor is also given to calculate the lake evaporation, and the seepage loss from the reservoir during this period in hectare meter is. Now seepage loss we have to calculate. Okay. The same, it is water budget methods problem only. So let's see this. So for this delta S, it is given as minus 20 centimeter. And first we will take the precipitation, then we will take the inflow. Inflow, that is V inflow is equal to V outflow plus seepage loss that we have to calculate, and plus evaporation that is occurring, and plus delta S. Okay, this delta S is negative actually. So let's put the values. Precipitation is given as 3 centimeter. Okay, plus velocity in volume inflow. So 10 hectare meter. So let's convert this into meter. 10 into 10 to the power 4 meter. Okay, and then divided by this 1 hectare meter is 1 hectare is equal to 10 to the power 4 meter square. So 10 to the power 4 meter square into 1 meter. This is the volume in meter. Okay, divided by we have to convert it into centimeter. So 10 to the power 2 by, again 1 kilometer square area is given. So 10 to the power 10. So moving on to the next problem. This question was asked in the year 2003. The plan area of reservoir is 1 kilometer square. So plan area is given as 1 kilometer square. The water level in the reservoir is observed to decline by 20 centimeter. So here it is mentioned that delta S is negative. Okay, that is minus 20 centimeter in a certain period. During this period, the reservoir receives a surface inflow of 10 hectare meter. Now this is volume, it is given in hectare. Now 1 hectare, you know that it is equal to 10 to the power 4 meter square. Okay, so 10 to the power 4 meter square into 1 meter, that is, this will get as 10 to the power 4 meter cube. This will be the volume, and we have to convert it into centimeter. So it will be 10 to the power 6 centimeter cube divided by, we have to convert it into 1 kilometer square area into again centimeter square. So it will be 1 into 10 to the power 10. So this you will finally get as 1 unit. Okay, so 1 hectare is same as 1 unit here. So let's see this again. Let's go and read the question. And 20 hectare meter are abstracted from the reservoir for irrigation and power. So for irrigation and power, we 20 hectare meter is abstracted. The pan evaporation is 12 centimeter. Okay, and rainfall is 3 centimeter. Now pan coefficient is also given 0.7 to calculate the lake evaporation. The seepage loss from the reservoir during this period. Now again, this question is of water budget method. Okay, there we have the precipitation first plus depth inflow is equal to depth outflow plus we have seepage loss. Okay, loss plus delta S, and then we have evaporation loss. Okay, so precipitation it is given as 3 centimeter. Okay, plus velocity inflow. Now 10 hectare meter, we will convert it into 10 hectare meter is 10 to the power 4. This will be meter cube, and then we will multiply it by 10 to the power 6. This will give in centimeter cube divided by area in centimeter square. So this will be 1 into 10 to the power 10. So this will get cancelled. We will be left with only 10. So that's why I was telling 1 unit. 1 unit directly we have calculated 1 into 10. 10 hectare it is given, so 10 units. Okay, is equal to VO, V outflow. It is 20 hectare meter. So simply we can write 20 plus what is the loss that we have to calculate. Okay, and plus delta S. Delta S is given, it is declining, so it will be minus 20 centimeter. Okay, and then evaporation loss. For evaporation loss, it is given that you have to use this pan evaporation value. So 0.7 into 12 centimeter. Okay, so when you go on solving the problem, you will find the L value as loss, that is seepage loss. You will get it as 4.6. Okay, this will be in centimeter. Now this again you have to calculate this in hectare meter. So this 4.6 centimeter as 1 hectare meter, it is same as 1 unit of this rainfall. So 4.6 will be the only answer. Or you can again convert it into, we can multiply it by the area and then get the volume in hectare meter. This will be same as 4.6. So the correct option is 4.6. Okay. Now moving on to the next. This is an objective question asked in the Engineering Services exam year 2007. Let's read the question. A standard ground-based evaporation pan corresponding to IS is installed at the banks of a surface reservoir. Okay. The water surface area on a particular day is 100 hectares. So 100 into 10 to the power 4 meter square. This is the area that is given. The recorded evaporation loss from the pan is 4 centimeter. Now evaporation loss is given as 4 centimeter. What is anticipated evaporation loss from the reservoir? So evaporation loss we have to calculate in volume. So this is 4 centimeter. Then we will multiply it by Cp into evaporation loss, pan evaporation. This we will get as 4 centimeter. We know that Cp value for IS is 0.8. So it will be, it will give us 8 4s are 32. So 3.2 centimeter. Okay. And then we have to calculate it in meter cube. So 100 into 10 to the power 4 meter square into 3.2 into 10 to the power minus 2. Okay, this will finally get as in meter cube, and its value will be, you will get as 3.2 into 10 to the power 4 meter cube, which will lie in this range. Okay, option C. So 3.2 into 10 to the power 4 meter cube per day. This is the correct answer for total volume loss that is occurring. Okay. So let's move on to the next component, that is transpiration. Okay. So after studying, till now we have studied about precipitation and its measurement, evaporation, and just now we are starting transpiration. Okay. So what is transpiration? You all know it is the process by which water leaves the body of a plant and reaches the atmosphere as water vapor. Now this may be occurring from either leaves or the stomata. Okay, stomata are actually the pores which are present in the leaves. Okay, so the plants respire using these stomata. So loss of water also takes place through these pores, and maximum transpiration occurs during daytime. Okay, this because a lot of energy is available, the sunlight is available during the daytime, so around 95% of transpiration occurs during daytime itself, and measured using phytometer. This phytometer is actually a device to measure the transpiration. Now there are various factors affecting this transpiration. It may be atmospheric vapor pressure. As the atmospheric vapor pressure increases, you know that it will put pressure and will not allow the water to escape from the stomata, so it decreases the transpiration rate. Next is temperature. Okay, so the next is temperature, and temperature we have, if we go on increasing the temperature, you know that the energy rises and more transpiration loss. Third is the wind factor. If we go on increasing the wind velocity, then transpiration increases. And fourth is a characteristic of plant. It depends on the type of plant and its morphology. And last is the light intensity. Okay, so this was transpiration, and it is just important from theoretical point of view. And for more important is evapotranspiration, because it combines both the transpiration as well as the loss of water which occurs from the soil which is surrounding the plant. Okay, that is evapotranspiration. So evapotranspiration, it is a sum of water loss to the atmosphere by plants through the transpiration, okay, and water evaporated from the soil or water surrounding the plant. As I told you, transpiration plus water surrounding the plant. It is denoted by consumptive use. Now this consumptive use, it involves both the evapotranspiration and the water required for metabolic processes in the plant. Okay, so this metabolic process, very less water is required, so it isn't calculated much, it is neglected. So directly we denote the evapotranspiration as the consumptive use of the plant. And PET, this we have already studied. PET is potential evapotranspiration. It is actually the evapotranspiration which is occurring when sufficient moisture is available to the plants. Okay, and it depends on climatological factors rather than on characteristics of plants and soil. So it doesn't depend on the characteristics or morphology of plants and soil, rather it depends on the climatological factors like the climate or weather conditions. And AET, that is actual evapotranspiration, naturally it will be affected by characteristics of soil and vegetation. Okay, it depends on the soil properties. And one more thing you have to realize here, for the ratio of AET by PET, when sufficient moisture is available, then it is approximately equal to 1. Okay, and if the moisture goes on decreasing, then this value also goes on decreasing, because actual evapotranspiration, this goes on decreasing, and potential evapotranspiration, this will always remain constant. Now let's see one more graph regarding this, how it depends on different types of soil. AET by PET ratio. Okay, and here we have moisture. Okay, percent available moisture available. So this will go on increasing. Let's say this is 0. Okay, this value is increasing as this is given as percentage. Okay, here, or we can take as fraction as well. And here in x-axis it is starting, firstly it was 100% moisture available, and then it goes on decreasing here. So it is decreasing on this side. So what happens? this graph you will, for clay soil it is observed as, for let's say this was unity at present, and when 100, as I told that when 100% moisture will be available, then AET by PT ratio will be equal to unity. So it first was that it will go on decreasing, and it will reach this value when 0. Okay, and this is case for clay soil. Now what happens in case of sandy soil? Sandy soil, we have less moisture holding capacity, so this will be less than of clay soil. Okay, this is the case of sand. So this is how the soil characters affect the AET and PET ratio. Now some terms which may be helpful. These terms may also be helpful in irrigation engineering. So let's see field capacity. Now what is field capacity? It is the maximum amount of water which the soil can retain with itself. Okay, so let's see this. This is the ground level, let's assume, and till here we have the field capacity. That is the maximum field capacity, that is the maximum amount of water which the soil can hold. This is the OMC, that is optimum moisture content. That the above this, this is actually the optimum level of moisture that must be supplied to the crop so that it can have the maximum harvest. Okay, and then we have the PWP, or the permanent wilting point. If water goes below this point, then the crop may decay. Okay, so it has to be above this permanent wilting point. And this we have the readily available moisture, because this water can be extracted using evapotranspiration, and this we have non-readily available moisture, because this below OMC, as I told that if water goes on decreasing, then there will be low harvest. So it has to be maintained above OMC. Now let's again see the proper definitions. For permanent wilting point, it is that moisture content below which water is not easily available for plant growth, and due to which the plant may wilt up, that is decay. And what is optimum moisture content? Moisture content in the root zone below which water is not easily available or not available at all. Okay, so not, as I told, non readily available moisture. If moisture is below OMC, then naturally low harvest. Okay. Now how measuring this? How to measure this evapotranspiration? Okay, we just go on saying that we measure velocity inflow and velocity outflow, but these are very tedious jobs. How to measure this groundwater inflow? These are very I may say these are very difficult to find. Okay, so let's see this, how to find this. We can just estimate these values. We cannot actually find the accurate value. So lysimeter method. Lysimeter, what it is? It is actually a special water tank. You may see this is a special water tank containing a block of soil, okay, and set in a field of growing plants. So we replicate the exact conditions of the plant growth in a certain special watertight spherical tank, okay, and we replicate the soil conditions, moisture conditions, and then evapotranspiration is estimated. And how is it estimated? In terms of amount of water which is required to maintain that constant moisture conditions within the tank. Okay, so the we just go and pour the water and allow the crop to grow or the plant to grow, and the amount of water, excess water which will be seeping through the ground, that will be collected, and then that we can calculate, and that will be the excess loss of water that is taking place, or evapotranspiration. Okay, so this was lysimeter method. Now let's see the field plots. This is a generic method. Elements like precipitation, irrigation input, runoff, soil moisture, and percolation is measured for a plot of land. Now these, as I told, that these are very difficult to calculate. So evapotranspiration, it can be directly calculated as precipitation plus irrigation input minus runoff because it is occurring, it is actually loss, so runoff minus groundwater loss. Okay, so this is evapotranspiration, and it is not a very reliable method because, and it also involves huge cost in calculating these all separately. Okay, so this was field method. Now coming to another method, that is Penmans equation. This is an empirical method. Okay, and it is obtained by combination of energy balance and mass transfer approach. Okay, Now this point is the most important point, because directly many times, around 4 to 5 times, yes, they have directly asked this question. Penmans equation is based on these, either mass transfer, energy transfer, water transfer, or energy balance and mass transfer. Okay, so the correct option is energy balance and mass transfer. Both are responsible in this forming this Penmans equation. Now this is the Penmans equation, that is it gives the value for potential evapotranspiration AHN plus EA gamma by A gamma. Now what is A? A is the slope of saturation vapor pressure versus temperature curve at mean air temperature. What is HN? It is the net radiation, that is millimeter of evaporable water per day. Okay. EA is the parameter including wind velocity and saturation deficit. Okay. And gamma is the psychometric constant. It is considered as 0.49 millimeter per degree Celsius of mercury. Okay. So you don't have to you don't have to remember this formula, because it is generally not asked directly in the question, but just have an overview of this. Okay, on what factor it depends. So we come to the end of this video. Hope you enjoyed it and gained enough info from it. In the coming video, we'll be starting with next component, that is infiltration, and we'll be seeing on some cumulative infiltration curves and Horton equation, and how to measure this infiltration values. So the next video will be very important from the gate point of view, so do watch the next video. You can also practice free quizzes at Gradeup and always be a grade higher. Thank you and all the best.